Okay, so let's complete our development for the formula of the surface area of a solid revolution. Where we left off in the last video, we had just found a formula for the area of a frustum of a cone. So this surface area here is what is approximating the area of the actual solid in our subinterval. So we've got 2 times pi times r, which again is just the average of the 2 radii, and then L, which is that slant height of our frustum. So our goal now is to reinterpret this formula for the area of frustum using x values and function values in our scenario. So let's just take a quick look here back at our original diagram. So here we've got our L, which is just the length of the secant joining the 2 endpoints, and then our R1 and our R2 are just our function values. Okay. Now, as we said in the last video, we don't want to be working with this R1 and R2 with these function values at the endpoint. Our goal is to eventually work with some random CI in the subinterval. So let's start now building our Riemann sum, and we're going to start with our usual building blocks. So we've got let P equals x naught, x1, all the way to xn, okay, be a partition of AB. Right. We have our delta xi, as usual, is just xi minus 1. Now in this case here we do need those endpoints, so we'll let pi be the point xi yi, where y of course is that function that we're revolving around the x-axis. Okay, so what we need to do now is again reinterpret this expression here using these building blocks. So we'll start with the L. I think that's the more obvious one. So that is just the length of the secant joining the 2 endpoints. So again, I'm going to be using this notation which represents the distance of the segment joining these 2 points. Now this is where I'm going to skip a whole bunch of steps because we already found a very nice expression for this length. If you think back to our work with the length of a curve, okay, we were able to come up with this nice expression. So square root of 1 plus, and we had the square of the derivative of our function, okay, and what was nice is that it was evaluated at some ci in the interval, okay, and this was all times the length of our subinterval delta xi. So let's recall that ci is some value in the open interval xi minus 1 xi. Now you might be wondering, why is it the open interval, not the closed, as it normally is. Recall that we used our old friend the mean value theorem to generate this ci, which is why it needs to be in the open interval. So now that we've taken care of L, let's see what we can do with R. And this is where we use a little clever trick. So I'm going to bring back our old diagram here, and the idea is R represents the average of these 2 function values. Well, remember that these subintervals are getting smaller and smaller and smaller. In other words, that these endpoints are getting closer and closer to the ci that was generated earlier. So what we do is we approximate the average of these 2 function values by just the function value at ci. Okay, so let's finish that off. So we're going to approximate that with f at ci. So now we've accomplished what we needed to, which was to rewrite each of the variables in this expression using either x's or function values. So let's bring this all together. So the area of one of those frustums for a particular subinterval can be written as 2 times pi. R again is being approximated by f at ci. Okay, and we've got L, which we're using this nice expression, 1 plus the square of the derivative at ci times delta xi. And if we want an approximation for the total area, we just sum up all of these individual expressions. So 2 pi f at ci times our nice square root expression. And lo and behold, we have exactly what we were looking for, which was a Riemann sum. Now, similar to what we saw with our work on the length of a curve, what we need in order for this to be integrable, ideally, is for f prime to be continuous, because then the square will be continuous, and here we have a sum and a square root, again, all continuous. If f prime is continuous, we know that f itself would be continuous, and so in the end, continuity of the derivative will ensure continuity of this whole expression. So we can write, if f prime at x is continuous, then we can now extend this to an exact expression for the area, which is just given by the integral from a to b of 2 pi. F at ci, of course, becomes f at x in the integral, and this becomes the square root of 1 plus the square of the derivative. And of course, our delta xi becomes dx. And here we have it, again, the use of the definite integral to find a fairly common measure, such as the surface area. As we've done in the past, we say that this can be easily adjusted in case you find it easier to integrate with respect to y. And so there we have it, the formula for the surface area of a solid of revolution.